Now, in August 2022, we released VisiView 6.0. It comes with a ton of new features in all aspects of the software. We implemented new acquisition modes like the region view and the virtual camera for surf and sim imaging. We gave the user interface more clarity in the selection of illuminations and the display of image data. And artificial intelligence also found its way into VisiView. We use it for improving images and finding objects. Last but not least, we put a lot of effort in supporting two new devices, the Mamatsu Micro resonance scanner and the Crest Deep Sim. A completely new acquisition mode is the region view. It's the further development of the scan slide feature. It's more comfortable and more flexible to use, it's faster and more precise. The heart of the region view is the stage position viewer dialog. It's used to display the whole sample, to navigate over the whole sample, and to set up your scan slide experiment. Moving the stage around, you easily define your overview scan area. If the overview is ready, you easily can draw multiple regions which should be acquired later in high resolution. You also can decide on how many tiles should be acquired. If you change the magnification, VisiView recalculates the tiles. And imagine a large sample where you want to image two distant regions. It's rarely the case that they have the same focal plane, so it will be necessary to adjust the focus for each tile. And this is possible in VisiView. You can set focus points and the software calculates the focus position for each tile. Further, we implemented a virtual surf camera to facilitate surf imaging. Surf is a super resolution by radial fluctuation algorithm by Ricardo Enriquez. It calculates super resolution images from multiple noisy images. The virtual surf camera acquires these multiple images per time point in the background and directly calculates the surf image. With proper settings, you easily can achieve results like that. Besides these acquisition modes, we have some useful changes in the user interface. We extended, for example, the connection properties by a connection viewer. As you may know, connected images from one experiment can be synchronized in regards of scaling or zoom or timestamp, but now they also can be displayed in one view, in one window. This makes a comparison between experiments more clear. We also did something to clean up the elimination list and elimination devices. In some systems, the list of elimination devices and eliminations is very long and not clear. In the new configure elimination dialog, all the devices are collapsed and just expanded if they are part of the elimination which is activated. The eliminations themselves can be grouped by tags, and any user can decide on the write and read access to his own eliminations, except for the administrator eliminations. The elimination list can be also shortened by just limiting the visibility to the own eliminations or just to others or just to the administrator eliminations. Grouping and sorting of the eliminations is also reflected in the elimination list in the acquire dialog. Like for eliminations, we now use the administrator login also to protect the configured devices from unauthorized access. Have you ever wanted to repeat an experiment, but you forgot about the imaging parameters? We spent VisiView now a restore button, which restores all imaging parameters including the laser power. But not only imaging parameters can be restored, but also the information from microscopic images which are underexposed and thus noisy or blurry. For this, we use pre-trained artificial intelligence filters which are part of the processing. We have a noise filter, a blur filter, and a scattered light filter. Let's demonstrate their functionality with a few examples. Here we have a noisy Darby image, and if we apply the noise filter, the nuclei are smooth again. And the blur filter even enhances the contrast from super resolution images acquired with the Sora. But the most enhanced filter for image restoration is the scattered light filter, as you can see here from these noisy images of VisiView. These nicely restored images are a very nice template for object analysis. And this brings us to the next new feature in VisiView, the object analysis powered by artificial intelligence. Previously, the object segmentation was relying on equally intense objects with equal shape and orientation. But now you can train a neural network to detect objects which are not thresholdable, like in DIC images, and which may have a different shape in 3D depending on their orientation in the sample. In order to train the neural network and to create a model for object segmentation, you have to create a training data set where you draw the regions into the images around the objects of interest, and you can create multiple categories of objects and they can be all trained together. If you have done this, you can start a training and decide on the complexity of the algorithm. Usually within half an hour the training is finished and you have a model which you can apply to your samples. As you can see in these DIC images, our self-trained model reliably and quickly identifies the nuclei. At the end, I would like to direct your attention to two newly integrated devices. The first device is the Hamamatsu Micro MEMS confocal. It's a super compact confocal system which uses a MEMS mirror to quickly scan the sample with up to 80 frames per second. The system is so compact because the lasers are integrated in the confocal head. It comprises of up to 4 modules which all have a PMT, the optics, filter, pinhole and the laser. And that's the way you can acquire simultaneously up to 4 channels. The second newly integrated device in VisiView is the Crash Deep Sim. It provides 100 nanometer resolution imaging, even 50 micron deep in the sample. If you liked that video and like to stay informed, you should not forget to subscribe.